Right, module 4.3, electrical circuits. Okay, first bit of this module is Kirchhoff's second law. Now, if you remember, Kirchhoff's first law was at a junction, the current splits. What Kirchhoff's second law is to do with, it's all to do with energy. It's the conservation of energy. So if we've got a circuit with a source of EMF, and a couple sources or a couple places where energy would be released, the sum of the EMF would be equal to the sum of the potential differences. So if that EMF was 4 volts and that potential difference was 3 volts, that would have to be 1 volt. Now this works in a circuit, in a loop of a circuit. So even if this circuit came off and had another something down there, we could just look at this loop of the circuit here. Okay, in this loop of the circuit here, that 4 volts would split into whatever's over that one plus whatever's over that one. We could look at this loop of the circuit here, and it would split into sum over that one, sum over that one. So if you take a loop of a circuit, if you add up all the EMFs in that circuit, they would be equal to the sum of all of the potential differences in that circuit. So we might have some sort of weird circuit where we have a source of EMF, we have somewhere thing that you have potential difference over, another source of EMF, another thing for potential difference, and another thing for potential difference, and so on and so on. Now we look first of all at the things that would produce the EMFs. Say this one was 6 volts and this one was 3 volts. The total EMF in that circuit, the sum of the EMFs, would be, well, it would be 6 plus 3, wouldn't it? But if you look, this is round the wrong way. So this is like making the electrons come this way, whereas this is trying to force it back. So the sum of the EMF in this circuit is going to be 3 volts, because I've done 6 volts, take away 3 volts. Now the potential differences over that, and that, we know will add up to 3 volts. Okay, so make sure if we're using more than one source of EMF, have a look at the direction it's going in. If I added another source of EMF there of 1 volt, then I'd do 1 volt plus 6 volts because they're around the same way. But then I'd have to take off the 3 volts, which would give me an EMF of 4 volts. So make sure with several sources of EMF in a loop, you add and subtract as necessary. Now the next thing in this section is about internal resistance. What internal resistance is if we have a battery, a cell looks like that, doesn't it? The electrons have got to go through this cell, okay? So they've got to go through this cell. There's going to be some resistance actually within that cell. The chemicals within that cell will cause some sort of resistance. So if we have our circuit here and we pop a voltmeter over this bit here, it's not actually going to give us the EMF of the battery. It will give us the potential difference over the components in the circuit, but we don't know what the potential difference is over the battery. Now, the way they represent internal resistance sometimes in diagrams is just drawing a little resistor there to represent the internal resistor. Now, that's not quite true. As we've said up here, it should be in the middle of it, but that's how we represent it, and we sometimes have a circle around it to show that's the internal resistance. So, Kirchhoff's law now, the EMF over this would be equal to the potential difference over this plus the potential difference over this. Well, we can write that out. So the EMF is equal to the sum of the potential differences. So that's V, the potential difference over that, plus the potential difference over that. Now, we tend to write that because we call the internal resistance lowercase r, we call the resistance of the circle uppercase r, we could just write that V plus IR, where this is the potential difference over the resistor. So we could write it as IR plus IR, or indeed IR plus R. But you tend to get it given like that. So this is the EMF, this is the potential difference over the circuit, and R is the resistance of the circuit. And we've got IR there. But it does work, as I said, if you've got that as well. Now, what you need to know is the circuit that we use to actually try and measure the potential difference. And it's basically just this circuit here, but we put an ammeter in it, and because we want to change the potential difference over this resistor, we make that a variable resistor. So we can change the resistance in the circuit, measure the current. Now, and we're going to be measuring the potential difference as well. So what we use is this equation here, but to be able to draw it into a graph, we rearrange it to V is equal to E, take away IR. Okay, that's just that one rearranged. Now what we do is we measure, for different resistances, we measure V and I. And if we plot a graph of V against I, we get a straight line graph going like that. Now, thinking about it from this, using y equals mx plus c, that's what's on the y-axis, that's what's on the x-axis. So your gradient of the graph is equal to the internal resistance, and the intercept of the graph is equal to the EMF. Okay, so again, if you've got to do this as your experiment, you've got to write a procedure, you've got to write what the measurements are going to be, and an analysis. So that would form your analysis. Remember that you're going to be measuring both the current and the potential difference. You're going to be changing that. You need a circuit diagram to show that. Okay, last little bit that I want to go through is potential divider circuits, and that's how, well, really the EMF splits over different things in the circuit. So if we've got a source of EMF, and a lot of the times these questions, they say that internal resistance is negligible, you don't need to worry about internal resistance. Let's say we've got a 6 ohm resistor, and we've got another 6 ohm resistor, and we put them into a 24 volt supply. I hope you're okay that that supply will split 12 volts over this one and 12 volts over that one. Okay, what about if I change that from a 6 ohm resistor to a 12 ohm resistor? Well, what it does is it needs twice as much energy to go through that one as it does through that one. So 24 volts is an easy one to work out. That would have 16 volts going over it, and that one would have 8 volts going over it, because it's splitting in a ratio of 12 to 6. So that's splitting in a ratio of 2 to 1, isn't it? So I can work out, just looking at the numbers, what they would be. It could be that they give you less easy numbers. So let's say that that one's 12 and that one's 41. What you do then, the calculation you do to work out what the potential difference is over the 12, is you would do 12 divided by 12 plus 41. So that's finding the fraction that the 12 is of the total, and then multiply that by 24, by the EMF, or the volts that you've got to divide up. So that would tell you over the 12 volts, and obviously over the 41 volts, you do 41 over 12 plus 41, and times 24 for that one. And so there is a way of working it out. Now you might have to do it, instead of, if you've got a 2 fixed resistors, if this was, let's say it's a thermistor. Now what you'll have to know here is, in the dark, the resistance of the thermistor is higher. Okay, so this has got a high resistance in the dark. Now, if it's got a high resistance in the dark, it's going to have more of the share of the 24. So this is going to be lower. And in the light, it's going to have a low resistance, so it's going to have less of a share. So the potential difference over this would be higher. So over this fixed resistor, in the dark, because that's high resistance, it gets more, it gets less, that's going to be low. And in the light, that's going to increase. Now you also need to know about it with an L light dependent resistor. It's a similar thing. In the light you get a lower resistance, and in, oh, I do apologise, I've gone dark and light there, haven't I? I should have gone that that in the cold it has a high resistance, and in the warm it has a low resistance. So I hope you can follow through the logic. You do need to be able to do it for the light dependent resistor as well. Okay, now that's all of your electricity course, well, the main points that I looked at, covered in 2 videos. But if you've got any questions, please email, and I'm going to try and put waves up either later tonight or tomorrow. Okay, good luck with your revision.